others for giving me the opportunity to talk over several concepts we heard about already this morning, but I apologize for being completely classical. Right. This does not work. No, let's do it. Good. Yeah, I'm especially grateful to Olivier, and I thank him on my knees, like these other two guys here, for the pre-conference meeting we had yesterday. Many people will talk about YIG later, but I'm the first one, so let me introduce this material. It's a real monster with 18 atoms in the unit cell. It consists of a scaffolding of oxygen cations, which leave a lot of space for the yttrium anions, whereas the iron anions are in these octahedrous and tetrahedrous, which you see here. These octahedrous and tetrahedral iron, they have a magnetic moment of a spin of 5½ They are strongly antiferromagnetically coupled. But you have more of the tetrahedrous than the octahedrous, so the whole system is magnetic. It's a ferrimagnet. So yttrium iron garnet is a very nice material. It's basically the best ferromagnet there is, if you count it in terms of the magnetic quality factor, the quality factor of the magnetization dynamics. It has many applications, real applications, because of that. So, now this is quite interesting, the history. It's since YIG is not seen in nature, it has been discovered by the French, but all the patents are with Bell Labs. You see below the citation index here. Here it starts, then it was sort of saturated for a long time, and around 2010, 2011 something strange happens because the field explodes. Guilty for that is my colleague Eiji Saito. He will speak in this session because he had this brilliant idea to put electric contacts on this magnetic insulator. Okay, let me tell me a little bit about what I think is spin mechanics. And it starts basically with the Landau-Lifshitz equation and Neutron's equation. We heard already about the Einstein-de Haas effect, which basically is conservation of angular momentum. We also have a reciprocal effect, which is the Barnett effect. And in the absence of anisotropies, these two equations are coupled by the magnetization damping, by the Gilbert damping, and the equation we have to solve, the dynamics for a magnetic nanoparticle in the classical limit would be something like that. Now these Barnett and Einstein-de Haas effect are important in generally for larger frequencies. In the condensed matter, we usually do not have to worry about that. The most important dominant term is the spin lattice interaction term, which comes through magnetoelasticity and magnetostriction. This problem has essentially been solved long time ago by Charles Kittel. Here is the formulation in the modern form, which you can look up in this article by Flebus. So you can diagonalize this Hamiltonian, which is an 8×8 matrix, and this term here is a diagonal matrix which contains the eigenvalues of our problem. Now this can be easily calculated for YIG parameters here. You see that we have a parabolic magnon dispersion here. There are the TA and the LA phonons. The magnon dispersion can be shifted up and down with the magnetic field relative to the phonons. Now, if you look closely at these crossings here, you see the effect of the magnetoelastic coupling, which is actually pretty small in YIG. So this is basically the basics of spin mechanics. Let me just review a little bit about the previous episode 1 year ago when we had Spin Mechanics 4. So at that time I reported results from Simon Streib on the FMR spectra of magnetic nanoparticles, which showed satellites due to this Einstein, de Haas, and Barnett effect. Ka-Shen had explanations for pump probe magnetizations on thin films of YIG. I will review it just in a second. We will hear more about it from Professor Saito, I think, but at that time we just discovered the magnon-polaron anomalies in the spin-Seebeck effect. Now there are many more recent developments as well. Let me just mention these ones here from the Resende group, which in an inhomogeneous magnetic field could transform a magnon in a phonon at this magnon-polaron crossing. There is an interesting experiment by the Tula-Purka group, which showed reciprocity of photon-magnon conservation in such a structure. And of course, there will be many interesting presentations still at this conference and posters as well. Now let me go into more detail about recent work by Ka-Shen. He is now at Beijing University. He has been studying pump and probe dynamics of YIG films. So there is a pump laser which is focused on a spot, and with a probe laser, these experimentalists, they scan the sample and get a spatiotemporal image of the magnetization dynamics of the Z component of the magnetization, which has been excited by this pump. And you get pictures like that, where you throw a stone basically into the pond and you see how the waves are moving outwards. Now the excitation can be done in principle by three processes: the inverse Faraday effect, which is not important here because the experimentalists do not see a difference between plus and minus polarization. It can be heating of the lattice, which is our favorite model. We cannot completely, there might be some contributions to demagnetization by the laser. Again, detection is now standardly done by Faraday and Kerr. So what are we doing here? This is the laser who comes in and hits the thin film. And usually it is a very fast laser. That means it's basically a theta function type of temperature increase. It has a certain spot size, which is governed by the focusing, which is of the order of microns. And there is some decay time, which we take to be long later. Now what happens then from the mechanical point of view? We have this hot spot at the center, which heats the lattice and tries to expand the lattice in all directions. Yes? I actually do not exactly know what the frequency is, but I guess it is being absorbed, so it's just getting hot. Yeah. Okay, so yeah, so it's getting hot, and you have to solve the elastic equations of the system, which you can do separately for the transverse and the longitudinal ones, for the pressure and the shear waves. And yeah, what you need here, these are basically the source terms in this case. And the parameters are the elastic constants of the system. Now, because of the magnetoelastic coupling, these deformations, RL and RT, they cause effective magnetic fields, which then act on the magnetization and cause the magnetization dynamics. Delta 1 here is the magnetoelastic constant, which is well known for YIG. So the excitation spot size is a parameter which can be changed. The rise time we assume to be 0, whereas So the lower ones are the transverse ones. So we see they have different phase velocities and different group velocities. Now the group velocities are exactly the sound velocities. So what we see here are the phonons. They are expanding, and because at the phonons you have these magnetoelastic effective magnetic fields which excite the magnetization. So the magnetization, what you see here, is basically the phonons. Now this technique was then later developed further by Yusuke Hashimoto from the Saito group actually, and he saw much more fine structure in his experiments, as you see here, for example. So the reason for that is that these Yig samples have a much lower damping than the previous ones by Ogawa. What he then does is he Fourier transforms everything from real space in time to reciprocal space in frequency, and he gets this nice dispersion relation in which he can really observe the dispersion of the phonons and the magnons, and he calls this Swat, spin wave tomography. So we tested now our method and see whether we can explain this as well, and this works actually quite nice. Here we see now for a lower damping the excitations after 4 nanoseconds in this case, for shear waves, for pressure waves, for different spot sizes, because you need a focus beam in order to reach these crossing points, this magnon-polaron type of excitations, and magnetic field. If you have a large magnetic field, you can shift these crossings out of reach of the optical spectra. The spot is this one here is 2.5 micrometers, which is a little bit broader. This one here is more focused.
How much is the temperature?
This is room temperature.
Well, but you are saying that it's the heat.
Yes, it is by the laser. There's a laser pulse.
How much does the temperature?
Oh, this is not known. This is so we do not worry about the absolute size here. We just yeah. It's
fraction of a degree or significant?
Oh, that can be tens of degrees. This order of magnitude. Yes, yes. Oh, it's at the spot. It's certainly not linear. But as soon as they evase, get out of the spot, then you get very quickly in the linear regime. In the spot itself, it's certainly not linear. Now, that's an interesting technique also developed by Hashimoto, which is called the Gabor Spectra, in which you look basically at the Fourier transform as a function of time. So it's a sort of a mixed representation of the real space and reciprocal space. And here you see that in a function of time, how, for example, how these crossing points, these magnon-polarons, develop for the small spot sizes, and we get a very nice agreement with the experimental results in this case. So we believe that we do understand all these experiments, almost everything, by spin mechanics, by heat-induced deformation of the lattice, which then excite the magnetization. We cannot completely exclude demagnetization. It has the same symmetry as the pressure waves, and both effects might be mixed. The second topic I would like to discuss are some very recent results from Simon Streib from Delft on a phenomenon we call phonon pumping. So spin pumping, I think it's now a pretty well understood phenomenon, namely that magnetization dynamics will pump a spin current into a metallic contact, like indicated here. So this is then a spin accumulation, and this has different type of effects which can be detected and manipulated and so forth. Now what happens if this contact is not metallic, but it is an insulator? It can be the substrate, for example, or something else. So what happens if we have magnetization dynamics? Now, and we didn't realize that, but this effect is known already for a long time. Magnetization dynamics can create sound. It can create phonons. Yeah, the humming of the transformer is actually also something similar, right? Where magnetization dynamics is by magnetostriction is transformed into some audible signal. Now here it's the same. We know that magnetization precession will inject phonons, yeah, this was discovered first by Bömmel and Ransfeld, and Comstock and Kroh had already a theoretical description of this effect. Now, so what happens if you have this magnetization dynamics? In an adiabatic limit, the lattice would like to follow the magnetization in order to get the minimum energy conformation. Now, this can do it in two ways. It can either by rotation, a local rotation to the magnetization, or it can accommodate this magnetization by a deformation. So these are basically two different independent effects which should be taken into account. Right. And if this precesses, these two are coupled, of course. Again, basically the theory is known in the literature. So the magnetization, magnetoelastic energy, in the case of this deformable continuum elastic medium, can be written like that. We have a volume integral. These are the components of the magnetization. And we see here these two effects. These are the magnetoelastic one. So they react to the strain tensor, to the deformation of the lattice, and there is this one reacts to the rotation of the material. This is the rotation tensor. Now this is a complicated equation which can be simplified a lot. First of all, by assuming that B is along Z, we take a simple cubic material along 1, 0, 0, and we only look now at FMR of the Kittel mode, which means that the magnetization is now constant over the whole magnetic film. So if we look at spin waves, these things get more complicated. Now if we do that, we can simplify this equation to this equation here, where now the difference between this rotation and the deformation vanishes. So we got a combination of these contacts, and this one here is basically the same as what Carsen called small b, and this is the anisotropy constant. Now what we see here is a summation, is an inner product of the shear strain at both edges of the magnet, at 0 and minus d, and this is the magnetization here, basically an inner product. Now with this expression, you can calculate the dynamics of the system. Now, what we then want to know is what happens if we have now the system coupled to some insulator, to some substrate. And clearly, if this magnetization moves and the lattice moves, then also this will be transported to the contact. Now, yeah, so we know the differential equation for the magnet itself. So we know also the dynamics of the conventional insulator. We just have to formulate the boundary conditions, which are continuity and conservation of the flux, taking into account the forces at the boundary due to the magnetoelastic interaction. And now, then we can simplify by saying, okay, let's assume that the elastic constants of these two are exactly the same. And then the expression for the additional damping, and this is the main result actually, the additional damping due to the emission of phonons comes out to the expression like that. So, yeah, this is the additional damping parameter which comes on top of the conventional damping of the material. Now, what do we see here? Omega c, this is basically the coupling constant we saw before. This is the omega r, this is the ferromagnetic resonance frequency. Now, then we see here some material parameters. This is the thickness of the magnetization of the magnet, which is, as always the case, because it's a surface damping. If you make the magnet thick, then the relative effect becomes small. Now, interesting here is this term here, which is a geometrical term. And this one here has maxima when the sign is also maximum. So this happens when the precession frequency of the magnet resonates with the phonons, or in this case the transverse phonons only, and we see that we get the maxima at these frequencies. It's also interesting to note that this damping constant does now depend on frequency. So this is something which does not agree with what people call the Gilbert phenomenology. In the Gilbert phenomenology, the alpha is a constant. It does not depend on frequency. So we have to conclude that this phonon damping is a different. We do this basically in linear response, but we cannot write this as m cross m dot as we usually do for the damping. Right, these are done calculations for the parameters of YIG, which might not be the optimal material because these magnetoelastic effects are pretty small. Nevertheless, what you see here as a function of the magnetic film thickness here, and as a function of the FMR frequency, which can be tuned by a magnetic field, for example, we see that we have, first of all, these are the resonances I was talking about, at which the frequencies, they match the transverse phonons. And the maximum here becomes something like 10 to the minus 3, which is already quite relevant for very high quality YIG films. I should mention that there is also the torques due to this phonon pumping. They are damping-like and they are field-like. There's also a small field-like component, which is indicated here. It's not very large. It measures in microtesla. So this is a damping which we always have if we have a thin film of YIG on a insulating substrate, which becomes more important if you go to thinner films, and the increased broadening which people measure might be partly due to this effect. So then we come already to the take-home messages. So the spin mechanics in YIG basically is basically understood for a long time, but we still find surprises and new results coming out of it. We understand that the fast optical excitations by laser, focused lasers, they are caused by heat-induced lattice strains. If you have large magnetization damping, what you basically see is the phonons. You detect the phonons by the locally excited magnetization. But you also see all sorts of spin waves if you have lower damping and strongly focused laser beams. Finally, magnetization dynamic pumps the phonons into insulators, and this increases the damping, but not according to the Gilbert phenomenology. So the next step would be to understand what you can do with this pumped phonon currents. You can, for example, couple two different magnets with it in multi-layer systems. Okay, so let me finally allow me to make some advertisement for another workshop, which might be interesting for a subset of you. It's spin cavitronics. It's spins in cavities in all sorts of in microwaves or light cavities or something like that. Okay, so thank you very much for your attention.